Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. What's new in the world of science then?
Well, it's a sort of breath of fresh air week this week because there's two really hard-hitting and exciting papers on lungs. And researchers at Harvard have come up with a way of making a lung on a chip, would you believe? This is a microscopic lung which, to all intents and purposes, behaves identically to lung tissue. But what it enables researchers to do is to test out how lungs work, to test the kinds of drugs that you might want to put into lungs, and also test out theories of how pollution and infections harm lung tissue, but without having to harm any animals or do tests on people in the process. So it's a very cheap and convenient and very clever way that they've done this. What they've done is to take a tiny block of material, and they've made a hole through the middle of the block of material and stretched across that hole a layer of a membrane which is completely porous. It's a chemical which is called polydimethylsiloxane. It's just an organic membrane which has holes in it so things can stick onto it but pass through it. And then on one side of this membrane they sprinkle on the kinds of cells that you find lining the airways of the lung. On the other side, they sprinkle on the kinds of cells that you find lining blood vessels, and then they fill the blood compartment with blood, and they fill the air compartment with air, and by stretching the block, they can make the lung pretend to breathe. But these cells behave identically to lungs in a real lung.
Wow.
And so you can do various tests and show how gas moves from one surface to another. You can put in bacteria, as they did, and show how the immune system actually comes out from the blood, and white blood cells go into the airspace and kill the bacteria. And they can also start sprinkling on nanoparticles, the kind of things that we breathe in from polluted air, to see how they cause inflammation and damage to lung tissue. So this means you can do these kinds of experiments very reproducibly, very cheaply, and you can make all the kinds of measurements that would be very difficult to do in an animal. So it's a big step forward and a very big cost saving, and also prevents us having to resort to very costly animal research.
Dr. Chris lined up firstly on the phones. We've got Dom in Newmarket. Hi, Dom.
Hi, Sue.
What's your question?
It's how are crisp flavours made?
The answer is it's down to clever chemistry. The way that things and flavours and tastes work is that if you have a look in the mouth, you find taste buds, and if you have a look in the nose, you find nerve cells that are sensitive to various chemicals. And the way in which we experience food isn't just things that we taste with our tongue, it's also an olfactory experience, it's a smell too. So when you want to recreate that experience, you have to find chemicals that are either identical to the stuff in nature, or you find a chemical that looks at a molecular level very similar to the thing that has the taste that you want to copy. So, for instance, if you know the structure of a taste receptor or a smell receptor in the nose, and you know what sorts of molecules it wants to latch onto to create that sort of smell or taste, what you do is to then make a molecule which can be made simply and will lock onto that receptor and fool it into thinking it's smelling the real thing, when in fact it's smelling your surrogate one. And so it's all down to manipulating different molecules to arrive at a combination that fools the senses into thinking it's experiencing the real thing. And people will do this with big tasting panels. They'll have groups of people who sit down and taste crisps for a living, and they will say, right, we want you to taste this flavour. First of all, they'll test if they even like the flavours, and then they'll start manipulating the flavours a little bit to try and get the one that gets the most people saying, yes, that tastes like X and is also nice. And that's how they do it.
Thanks very much, Dominic.
Okay.
All right, let's go to the phones now, because we got Chris from Norwich on the line. Hello, Chris.
Oh, good evening, Sue.
There you go, you're through to Dr. Chris. What's your question?
For about 20 minutes, a very large blue bottle fly flew into my window. About 24 times, in fact, I counted. Really hard. It was an audible crack. And it didn't fall to the ground, it just flew away and continued the exercise, and it's still doing it now. Why has it not killed itself?
If only. You know, fly spray works really quite well, Chris. Failing that, a newspaper rolled up works pretty well too. Yes, why don't flies commit suicide quickly enough? Probably the answer to this is flies are insects, they're arthropods, and therefore they have an exoskeleton. Their hard bit is around the outside, and the soft, squidgy bits are in the centre. Unlike humans, we have an endoskeleton, where our skeleton's on the inside and the soft stuff's around the outside. So this gives a fly a couple of advantages. One is the soft stuff, the delicate things, are protected inside by that hard outer shell, and two, that shell is made of a molecule called chitin, and this is a big polymer, and it's a little bit rubbery, so it will deform elastically to a certain extent. So when the fly cannons into the window, the fly doesn't have much momentum anyway, but the exoskeleton can behave a bit like a shock absorber and soak up some of the energy and the impact, and the fly just bounces off to a certain extent. Also, it has a number of proteins in its wings that are very, very resilient. In fact, one of them was cloned and copied in Australia about 5 years ago by a guy called Chris Elvin. And this is a protein called resilin, in honour of how resilient it is. It's the same stuff that's in, say, a bee's wings. And bees flap their wings 500 million times in the 3 to 5 weeks that they're alive. Amazing. And as a result, it's this protein which is helping them to do it. So basically, flies, insects, they're made of tough stuff, and they can fend off more than a car windscreen quite often, unless it's doing 60 miles an hour.
Oh, absolutely brilliant. Can we learn any lessons from that in the structure of vehicles?
Well, to a certain extent, yes, because obviously the difference between a fly and a human is there's a huge amount of momentum when a human is travelling fast because we weigh a lot more. But cars do exactly that. They crumple up. If you look at a car in an accident, cars are designed to soak up the impact by crumpling and deforming. And in the process of deforming, what they're doing is slowing down the deceleration that happens to the people in the car, because if a car goes from 60 miles an hour to zero when it has an impact, the people inside the car have to go from 60 miles an hour to zero as well, and if they're stopped suddenly by an impact with the steering wheel, that's obviously catastrophic. But if they slow down more slowly because the car is absorbing the energy, then this slows down the rate at which the people decelerate, and therefore they're much less likely to have severe injuries as a result. So cars are already kind of doing that. Other applications? Well, the guy I mentioned, Chris Elvin, who has managed to clone this resilin protein that's in bees' wings and things, he's interested in using this in replacing or repairing the vertebral column, the backbone, because between each of the bones are these protein-rich discs. They're squodgy like shock absorbers, and anyone who's ever slipped one knows that when they wear out, they're incredibly painful. And this protein, resilin, he thinks could make a very good substitute for some of the proteins in this disc material because it's so resilient. And he cites the fact that the average human bends their back about 100 million times in a lifetime, and since bees flap their wings 500 million times in a lifetime, there should be more than enough redundancy and safety factor built into the molecule to make it useful.
Wow.
Brilliant. Thank you very much indeed. Thank you.
Well, thank you,
Pleasure.
Chris.
Thanks, Chris. Great question.
Well, let's now go to Keith in Peterborough, who asks, why do rotor blades on a helicopter and the propellers on an aircraft tend to appear stationary when they're at full speed?
Well, the reason for this is down to the strobe effect. Now, the way this works, if you think about it, if you imagine a wheel, a circular wheel, and I've drawn on the wheel an arrow pointing at 12 o'clock on a clock face, and imagine that I start the wheel turning so the arrow is twisting slowly, and I'm going to shine a light at that wheel to illuminate it, and I'm going to do that once every second. Now, if the wheel is turning very, very slowly to start with, I will see a series of snapshots of the arrow going round, albeit appearing to jump round, because it takes more than a second for the arrow to go all the way round. Are you with me so far?
Yes.
Now, if I turn up the rate at which the light flashes on and off, so I see a picture of the wheel turning at, say, twice every second, now what I'll see is the hand going round in smaller increments. If I instead turn the speed of the wheel up, so instead of it taking a second to go all the way around, it now takes, say, half a second, what I'll see is the hand appearing and then disappearing and reappearing back where it started again, if you see what I mean, because the light is illuminating the wheel at the same rate at which it's doing one complete revolution. So as a result, you see the wheel appearing to stay still because you see it, it disappears as the light goes off, it does one complete revolution and then reappears again. So when you are looking at objects which are moving very, very fast, you can only gather information about them at a certain rate. And because they're spinning so quickly, by the time your visual system has caught up and taken another sort of mental picture of the object, it's completed a revolution and come back to where it started. So it looks like you're getting a series of snapshots. This is usually exaggerated when you see, say, a car wheel turning illuminated by streetlights, because the streetlights are flickering on and off. The energy going into them is at 50 hertz, so the light is going on and off 50 times a second, so you're getting 50 pictures of the car wheel a second. And in old Western movies, you might have seen the cartwheels appearing to go backwards, and that's because the camera was taking 20 to 50 pictures every single second. And as a result, you were seeing the wheel appear to speed up, and then start to go backwards, because you were starting to see the wheel getting round to the next point on its turn before the camera took another picture. So it's an optical illusion.
Wow. Let's go to our phones once again and say a very good evening to Jill. Hello, Jill.
Hello, Sue.
Hi, you're through to Dr. Chris. What's your question?
Hello, Dr. Chris.
Hi, Jill.
My question is this. Why is it when ladies reach a certain age that we get facial hair? Is there a possibility that we could stop that happening?
OK, I suspect the age you mean is probably from about 50, early 50s onwards. Would I be right?
Really?
Well, it can happen about then. The reason I say that is because this is the age at which the menopause usually has begun in most women. And when women have the menopause, what happens is they run out of follicles, eggs in the ovary, and as a result they can't make new ones. And that's where the estrogen comes from in the body. So after the menopause, the amount of estrogen goes down a bit, and other hormones, therefore, can increase, and you get more testosterone-like action happening in the body. Certain hormones that have testosterone-like effects can increase a bit, and this can provoke and promote a bit of hair growth. And so sometimes you can get little bits of increased hair, especially in places where hair wouldn't normally grow, but does in men. Luckily, because the levels are quite low, it doesn't tend to be too much of a problem.
Okay.
OK, Jill.
Thank you very much indeed, Dr. Chris.
Thank you,
Thanks,
Jill.
Sue.
Pleasure. Nice to talk to
Bye-bye.
you, Jill.
Bye-bye. Dr. Chris, this is from Dave, who's emailed in to say he knows someone who has Asperger's syndrome and understands that it's in the spectrum of autism, although many famous people have thought to have had it, including Einstein and Alfred Hitchcock. So is the complaint hereditary, and is there anything that can be done for people with this illness? Chris?
Yes, it's a very interesting question. The answer is it's definitely hereditary. We have seen in the last about 2 or 3 weeks, actually, researchers in Oxford University and internationally publish a very big paper in one of the science journals, Nature. This is Tony Monaco, who's a researcher at Oxford University, and they have found maybe 300 or more genes now which are linked to autism. So it definitely runs in families, although it's not as simple as, say, inheriting a single gene and you get it, or not inheriting that gene and you don't get it. It seems to be more that there are combinations of genes, and it may well be there are combinations of genes and you also need some combination of environmental factors, perhaps to trip in or determine how strong the effect of those genes is. This is something which has been an area of intense study, because obviously there's something very wrong with people who have some types of autism, and we would like to know, because it's a developmental disorder, in other words, it's something that is wrong with the way the brain wires itself up. It may be that if we intervene at an early age in people who have a risk of developing autism, it might be possible to prevent some of the symptoms developing. Now, not everyone who has autism is affected the same way. It's what's called an autism, or we tend to refer to it as an autism spectrum. What that means is there are some people at one end of that spectrum who are profoundly affected, and there are people at the other end of the spectrum who are less affected. And they also vary in how well these people function. Some people, for instance, have only mild impairment, whereas other people are very impaired in certain ways. So it's a very heterogeneous condition. It tends to occur more often in males, but that's not to say that you don't get females who are affected by autism or its relative Asperger's. And it tends to be associated with poor social function, so people find it very difficult to relate to other people and other people's emotions. They find it difficult to understand or appreciate what would happen if they say something. What impact will that have on the other person? And for this reason, they tend to be very interested in things which are not social. They're very interested in how things work in shapes, in mathematics, and as a result, many people who have what's called savantism are also thought to be part of this autism spectrum. There are individuals who, for instance, can do calculations in their head to tens of decimal places in literally seconds, and it's inconceivable how they do this, but this means that their brain has in some way wired itself up a bit differently to a normal person, and this gives them these incredible abilities. But there is a cost, because there may be an underappreciation or an underdevelopment of other aspects of the way that the brain functions or of the world around them. So the answer is that researchers are studying it very intensely. They have found a number of genes that are linked to it. We obviously inherit genes from our parents, and therefore there is an heritable aspect to autism, and at the moment people are trying to understand how we might be able to intervene. But all we can do at the moment is to try to make life as good as possible, both for people who have autism, but also for the people who have to care for people with autism, because it can be very challenging.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. All right, let's go to our phones again now, because we've got Alan from Orpington on the line. Hello, Alan.
Hello, Sue.
Hello there, you're through to the very lovely Dr. Chris.
This is based upon you accepting that there is such a theory as the Big Bang Theory in the universe. If that is accepted, which direction do we look out from Earth to see where the Big Bang took place? That's the first part of the question.
Yeah.
And so would we have to sort of stand on the equator at some point and look out? I know it's spinning, but using that as a part of the Earth. Or do we stand on the poles looking up, or down on the South Pole? And if we are all moving away from that point, does that mean that the Earth, the Sun, the Moon, and everything is moving at the same speed away from that central point?
This is quite difficult to get your head around. There's no direction you can look in to see the Big Bang, because the universe didn't exist before the Big Bang happened, and when it did, everything that existed was simultaneously created, if you like, or sprung into existence,
Right.
and it's been expanding ever since. So yes, there would have been a point in space of creation. In other words, when the Big Bang sparked off the existence of the universe about 13.5 billion years ago. But before that point existed, and the universe therefore existed, there was nothing. Hard to get your head around that, because we can't really conceive of where something came from if nothing was there before. But this universe popped into existence with that Big Bang, where an intense amount of energy, which was infinitesimally small and infinitesimally dense and infinitesimally energetic, it would appear, suddenly got converted from a lot of energy into material mass, if you like, matter. And presumably antimatter, but we still don't know where the antimatter went, and that's where scientists, or what scientists are trying to solve with the Large Hadron Collider, the question of why everything around us appears to be made of matter. Where's all the antimatter then? Because we think they must have been made in equal amounts. And the universe therefore popped into existence and began to expand. There were asymmetries. It didn't just expand smoothly in a big sphere, if you like. There were asymmetries in the way that the particles began to arrange themselves, and so things began to coalesce in various places, and this led to galaxies forming ultimately, and the whole thing continues to grow. So the universe is growing all the time. It's getting bigger, and the further away we look in space, the faster it's growing. And what's actually growing is the space itself. So the Earth stays the same, but the distance between us and, say, Andromeda, although Andromeda's coming towards us, so a distant galaxy, is actually stretching. The space itself is becoming bigger, if you like, and we think that the thing responsible for that is a concept called dark energy. Dark energy accounts for about 75% of the mass of the universe, and we can't see it. We've no idea what it is, but it would appear that when space is made, it makes more dark energy, and this fuels this pushing apart of the overcoming of gravity, making space expand away from us. So if you tried to find the centre of the universe, you wouldn't do it, I'm afraid.
Right, but are we all still moving on the Earth, the Moon, the planets, the Sun, the stars? Are we all moving, still expanding and moving away from any central point, or are we just spinning in the galaxy?
Well, the galaxies themselves have movement, and relative to our galaxy, some galaxies are coming towards us, many galaxies are going away from us. And we know this because if you look at the light which is coming towards the Earth from distant objects in space, we can record the frequency or the wavelength of that light. And if you look at, say, the wavelength of light that comes from hydrogen, I'm just picking that as an example, but we know what wavelength hydrogen produces light at. If you look at the light from a distant object, the hydrogen is slightly stretched. It's a bit red, or a bit too long wavelength, a bit longer than it should be. And this is called red shifting. And this tells us that the light must be coming from an object that's going away, because as it's going away from us, the light waves are getting stretched out a little bit, making them appear redder than they should do. Other nearby galaxies are coming towards us. So the space is more complicated than just everything spreading out, because there's local organisation and disorganisation. There's local movement, but there's also, in the grand scheme of things, this grand expansion. And if you wind the clock forward billions of years, one prediction is that if the universe carries on expanding like this, what we'll end up with is a cold, dark space where all the stars have run out of energy and disappeared off of our horizon. We can't see them anymore, and we're just lonely, these little blobs of matter in space, and it's billions of light years in any direction to find anything else.
Thank you very much. That's a very good explanation. Thank you.
Thank you. Thank you very much, Alan. Yeah, great one. Now, Hazel has called and said, on the subject of facial hair related to the menopause, I still had my periods until I was way into my 50s. However, when I was in my mid-30s, I started to get facial hair and lost the hair under my arms. Why did this happen? How bizarre.
Well, hair and the follicles that produce it responds to hormones in the bloodstream. And as we age, one of the reasons why we get the facial hair that was referred to earlier by Jill is that you get a change in the balance of different hormones in the body. So one explanation in a younger person who starts to get hairier is there may be a condition like polycystic ovarian syndrome. This is where the ovaries produce a number of different follicles all at once, and so they tend to produce too much of a hormone, and they also produce too many androgens, testosterone-like chemicals, and this is why people who develop polycystic ovaries might complain of increased hair growth in places that they shouldn't, such as on the face, but also the skin can become a bit greasier than normal, and that means people can develop some spots and things, and so that might be another reason why this can happen. But as you get older, because the ovary, the performance of the ovary can drop and the amount of estrogen it can pump out on demand drops, this upsets the balance of hormones a bit, as well as can gaining a bit too much body weight if you put on a bit too much weight. Fat cells also make estrogens, and they can also churn out things that have androgen, testosterone-like effects, and so that's another reason why the hair distribution on the body can change. I can't really explain why the hair should have gone from under the arms, though, although a Bic razor may account for some of those changes.
Let's go to the phones once again, because on line 8 we have Tony. Hello, Tony.
Good evening, ma'am.
Oh, good evening to you. What's your question to Dr. Chris?
Right. I was in a programme, I think it was Tony Robinson was doing it, and it was about methane gas. And millions of years ago, it came from the bottom of the ocean because it got hotter and it melted. It was frozen, and they say it's still there. Is there any of it round about our seas, or is it still, it sounds a bit frightening.
There are these things which exist on the deep ocean floor. They're called methane clathrates. And scientists have been studying these in some detail because they're quite clever. They are watery cages. In other words, if you take certain numbers of water molecules, I think that the magic number is about 22 and 25 water molecules, H2O, they can be stuck together in such a way that they form a cage-like structure. If you can imagine a molecular ball where you've got objects stuck together to make a ball shape, and inside it is a little cavity. So these watery cages have a hole in the middle, and methane molecules, carbon with 4 hydrogens stuck onto the carbon atom, they're just the right shape to slot into the middle of this ball, which they stabilise. And as a result, you can, under the right conditions of high pressure, deep underwater, for example, low temperature, and a source of methane bubbling out through the seafloor, usually because there's organic matter which has sunk to the seafloor and is now being converted into methane by bacteria or other processes. As a result, that methane gets locked up into these watery cages, which form up into big blocks resembling giant ice cubes. And sometimes fishermen, especially fishermen up in the north, in the Bering Sea and things, if they sink their dragnets down, they can sometimes hook them up, and they bring up something that looks like a big chunk of ice. And this is a methane clathrate. And these hydrates are unstable. You can actually light them. If you put a match to them, they will actually burn. And the heat obviously destabilises them, so the gas escapes and burns, and then releases some more gas and burns. And it's very strange to see the concept of actually setting fire to an ice cube. But they do exist, and why scientists are concerned about them is, one, there might be a practical application. As we might be able to make these things artificially, it could make a very safe way to store large amounts of methane and transport it without the danger of high-pressure vessels, because normally to transport gases you have to put it under very high pressure, and that comes at a cost. The other is that these things can destabilise. If the undersea conditions change, this represents a massive reservoir of methane under the sea, which is totally uncontrolled and unrestricted in terms of its ability to escape. So if the sea warms up, if currents change, or something destabilises these clathrates, they can suddenly belch up in one convulsive burp, and enormous amounts of methane, millions of tonnes, could surface and then go into the atmosphere. And of course methane is a very potent greenhouse gas. It's perhaps 30 times better as a greenhouse agent than carbon dioxide. And for that reason, we would be very worried if this was going to happen on a grand scale. So scientists are studying them, they do exist, and there may be a practical benefit as well as a disaster waiting to happen if we don't treat them with respect.
What can we use them for, Doctor, though?
As nature has demonstrated, that you can turn water molecules into a molecular cage to trap a gas. So it could be possible, rather than just trapping methane, you could use the same technique that nature has uncovered to trap methane, to trap other gases, or you could just use it to trap methane. So scientists are very interested in these interesting arrangements of water molecules that are stable when they get together in this way.
Right, Doctor. Thank you very much.
All right, Tony. Thank you very much. Thank you for your question. Let's go to a text message this time. This is from Keith in Felixstowe, and he says, has there ever been an alignment of planets, or will it ever happen?
Well, the thing is that the planets do align themselves one way or another all the time. The solar system is 4.5 billion years old, and the planets have been orbiting since they formed shortly after the solar system first formed, and they haven't always been in the position they are in now. They have migrated. We know that Jupiter, for example, has migrated inwards a bit, and also that the other planets, Neptune and Saturn, they have moved outwards a little bit, and this is because of what's called gravitational interactions or gravitational resonances. All the material that's in our solar system, the planets, the Sun, the Oort cloud, long way out, and the Kuiper belt between the two, that material all interacts with itself and with other bodies gravitationally, and it causes these bodies to shift around a little bit. So the planets have been moving around with these sorts of resonances for many, many years. In fact, there was a very nice paper that got published in the journal Science last year. It was by David Minton, who's a researcher at Arizona, I think, and he and his colleagues were looking at the asteroid belt, which is between Mars and Jupiter, and they noticed that there were various holes in that asteroid belt, which had been spotted before by an American astronomer called Daniel Kirkwood about 150 years ago. But Kirkwood had spotted these gaps, but there were only very few of them when he noticed it. But what David Minton and his colleagues noticed was that if they tried to model, by making a computer program, simulate the evolution of our solar system, they ended up with the wrong number of holes, and there were rocks there that shouldn't have been. And the only way that they could actually make these holes reappear in the asteroid belt was by making the planets move around, Jupiter move in a bit, Saturn move out a little bit, to affect these resonances that made some of the asteroids come out of the asteroid belt and then go into the inner solar system and do things like bombard the Earth. So the point they make is it's really intriguing to see 4.5 billion years later, almost like footprints in the snow of the movements of these giant planets reflected in missing matter or missing material from the asteroid belt. So the planets have been on the move for a really long time, and they're going to continue to do so, well, for an even longer time.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.